All right, getting started. Sorry, I'm about 45 seconds late here, but we're good. We are starting with equilibrium and what Randy loves to call statics. That's what we're doing today. So just think about this. Randy has been studying this topic since we started the semester. If you have any questions whatsoever, he's your man. He is your man. So I love this picture here. If you look up online why women live longer than men, you'll find many things like this that show similar levels of risk. That is a ladder, yes. So, retarded. So, what are they doing here? What are they doing? I mean, just description-wise, and then why would we consider this crazy, and why does it work? So, what are they doing description-wise? Okay, using the way that the two gentlemen on the right, on your left, excuse me. It doesn't matter. Okay, to counter his weight, using the leverage. So why do we consider that silly or dangerous? Because
there's so many things that can go wrong there.
There's so many things that can go wrong. The physics says, yeah, that should work.
It does work.
Because as we'll learn, we're providing counter torques, and this guy here, who's the heaviest guy, is out here at the end providing a fairly reasonable counter torque. But what if that guy's a mess up? You know, like he loses his balance and steps off the ladder. Yeah, well, he's not wearing flip-flops. The guy one closer is wearing flip-flops. But, let's be fair here.
Yeah, if you just slips on his flip-flops,
And so that's why we consider it dangerous, because even though in theory this is safe, in practice there's so many things that could go wrong. I'll be honest, I am kind of risk averse at my age, especially when it comes to heights. So they have these things like you can walk out on a glass bottomed walkway.
But it's not.
It's what?
Isn't that not actual glass?
Well, plexiglass or polymer.
Isn't it like the stuff they use in the phones?
But yes, which is plexiglass. Otherwise known as polymethyl methacrylate, or they could use a different polymer like a. I'm trying to remember what the other common one is, but I can't. I'm afraid to walk out on those because I can see that this is something that is only this thick. I'm not afraid to walk on a bridge if it's not transparent for the most part because I have faith in what I don't see. When I can see through it, I don't have faith. This one here, you do have to have faith that the ladder isn't going to break. You know what? These ladders actually aren't made to be super strong under shear, but you have to have faith that that's not going to break, and faith that your buddies aren't going to
do stupid things.
Yeah, do stupid things like, hey, look, and step off, whatever. So that's the kind of thing we're going to be looking at today. So we looked at collisions in our last lecture, and in lab yesterday, you explored elastic and inelastic collisions. Hopefully that was beneficial. It should have been illuminating to see the things that I've been saying in class are really what happens. There's a lot of things that people know about collisions, like if I have two identical objects and they collide with each other and have an elastic collision, what does elastic mean now? They bounce off, returning all the energy. They know that they just swap velocities. And you actually see that a lot in a desk toy. A desk toy where you have the metal balls, and you have like 3 balls, and you drop one ball, it swings down, it hits here, and one goes flying off the other side. And what happens if you drop 2 balls? 2 of them go off the other side. What happens if you drop 1 from one side and 2 from the other?
Swap.
Yeah, it swaps. It's really cool and fun. The explanation for that needs to go down to the level that I talked about with the bouncing balls I used. Was it the last class period at the beginning? You have shock waves that are traveling through and transferring the momentum. And that's actually the level you have to get to explain what's going on with those. Although you can also just say, ball 1 hits ball 2 and they exchange velocity. So ball 1 stops and ball 2 starts moving. Ball 2 immediately hits ball 3. Ball 2 stops, ball 3 starts moving. The chain reaction continues. Okay, so that's what we covered last class period. This class period, we are going to move into looking at statics. So we're going to start with the conditions of equilibrium. Equilibrium meaning equal forces. I just looked up before class with David why we use the letter P for momentum.
It's messed up.
It's really messed up.
Isn't it rho?
No, it's P. And apparently it's because in German they use der Impuls to mean momentum. And I is already a reserve symbol because it stands for moment of inertia. And M is already a reserve symbol because it stands for mass. And so they use the third letter in impulse for momentum. Isn't that a good reason?
I mean, there was.
Yeah, random would be the only worst one I can think of. But I can think of a worse reason too. Just have to, yeah. Equilibrium. The librium has to do with balance, and that's why the constellation Libra has scales, a balance. And we use lb for our unit for force. That is, the pound has the unit lb to stand for that same Libra. I mentioned this because in the article about why we use P for momentum, the person apparently that he was responding to had said, I know they use lb for pound because of the constellation Libra. No, the constellation Libra and the lb for pound come from the same Latin Libra. Anyway, so equilibrium, equal forces. Torque, we'll learn about torque. What do you call torque, Randy? Moment, yes. Oh, Oksana, you're in that class too, huh? She must be, otherwise she wouldn't have been able to offer it up so quickly. We'll learn about the right hand rule. Something real important right now, just to get it out of the way. For the right hand rule, you do use your right hand. I had a classmate when I was in college who said, but I'm left-handed, so can I use my left hand? No. The left hand and right hand are mirror images of each other. If you use the left hand for the right hand rule, you're going to get the opposite direction. So just remember that when we get there. And then hopefully we'll get to working some statics problems. So, go ahead. Little roadmap for where we're going. So our conditions of equilibrium. Condition number 1, the net force is 0. So this is an example. On this celestial sphere, what would you tell me about the net force? 0. Why? How do you know that?
Because it's not on the surface.
Well, no, it is on the surface.
I'm sorry.
But it's not moving. Not moving is a case of equilibrium, but it's not the only case of equilibrium. Right? If it's not moving, its velocity is constant at 0. But equilibrium has the net force is 0, which in terms of our kinematic variables means Newton's second law, net force equal mass times acceleration. The acceleration is 0. So the key is the globe is not accelerating. I said globe, it's a celestial sphere. It has stars on it, not the Earth. If that celestial sphere was moving at a constant velocity, what would its acceleration be?
0.
And hence it would also be in equilibrium. Now, the class that Oksana and Randy's taking is called statics. They are studying exclusively static equilibrium, which is what we have there. Static equilibrium is where it's stationary and in equilibrium. And so that's why their class is called statics, because they're doing exclusively static equilibrium. So that's our first rule. The second rule is all new. And so my next slide is going to explain what that is. But it's the sum of the torques is 0, or net torque is 0. And so the first thing we have to do is understand what torque is. And here's a story that I think is very on topic. When I was a kid, my dad and my Uncle Jack, who is not the famous Jack Webb, he's another Jack Webb.
There's a famous Jack Webb?
Yes. There's also famous Richard Webb, right? I've got a star in the Hollywood Hall of Fame, or Walk of Fame, but it's not me. It's Captain Midnight Richard Webb, not physics teacher Richard Webb. Yeah, just look it up, Captain Midnight. Anyway, so my Uncle Jack and my dad were talking about a car, and they're like, oh yeah, that thing's got a lot of torque, yeah. And little seven-year-old pipsqueak Richard, because I was really short, so I was like a junior in high school when I started to run. I was like, Daddy, what's torque? Because I had no clue, right? And of course, when you're kids, you're very curious. And as scientists, you stay curious throughout your life. You don't let people drive it out of you. So my dad thinks for a second. He says, well, it's kind of like the amount of twist. Now, I was a precocious enough 7-year-old that I said to myself, Daddy must not know what torque is because that's a stupid definition. It turns out it was a good definition. Torque is the rotational force. So it's the amount of twisting force you have. So my dad's definition, it's one of those things that you think you're smarter than your parents when you're young, and then you grow up and you realize actually they kind of knew more than I gave them credit for. So in the case of this goalie stick, very funny looking goalie stick, hockey stick, you have two forces acting, one up here, one up here. What do you actually call that in your class? Oksana, Randy? A couple. You call it a couple when you have two equal and opposing forces that are not acting at the same location. Because it's a couple of forces that are somehow related. So in this case, this force would make it rotate that way. This force would make it rotate that way. So combined together, they're going to make this stick rotate like this. Even though these two forces are equal, so the net force is 0, it's still going to have rotation caused by these forces, so it's not in equilibrium. So that's what the second rule is the net torque is 0. So let's get to calculating torque. So torque has an equation. Torque is equal to R cross F. This is what we call in algebra, in linear algebra, a cross product. So we've already learned what a dot product is. That's dot D. We learned work is force dot delta X. It means multiplication if I don't have the vector sign. So for it to be a dot product, it needs to have the vector signs. A dot product is a product of two vectors that's multiplying which parts of the vectors? The parallel parts. So the dot product is multiplying the parallel parts. So that's parallel parts. And it gives us a scalar result. What does the word scalar mean? Not vector. It's no direction involved, just a magnitude. And so we could also write at the end of this is equal to force times delta x times cosine of the angle between the two. So that's the dot product that we've already studied. It's also called a scalar product because it's multiplying two vectors and getting a scalar result. But then we have the cross product. Torque is equal to R cross F as an example. So we've seen both of these equations with the blue one, what we've just seen. Once again, if you take away the vector signs, that would be R times F. With the vector signs, it means you're multiplying. The cross is important because it has two perpendicular lines. The cross product is multiplying the perpendicular components. So you're only looking at perpendicular parts you multiply instead of parallel parts. And you notice that it gives you a vector answer. So it's the perpendicular parts and it's a vector answer. So a cross product is also called a vector product. But remember, the vector signs are important. If you put R without a vector sign cross F, that just means multiplication. But if you have vector signs on both sides, then it becomes a cross product. Now, because it's a vector, I can put the magnitude of the torque. So absolute value means magnitude is equal to R times F times sine of the angle between the two. So that looks a lot like the dot product, except for I exchanged cosine with sine. Why? Well, when we first saw the dot product, I showed you that I could take the force and I could take the delta x, and delta x, if I have the angle between the two, the component is parallel, is just the delta x times cosine of the angle. Well, the part that's going to be perpendicular would be the delta x times sine theta. Now, if you look at this and you think about it for just a second, I have force dot delta x and r cross f. Distance dotted with force or distance crossed with force. They're different things because one is multiplying parallel parts, one's multiplying perpendicular parts. What were the units for work? Joules. So we had a Newton meter equaled 1 joule. What are the units going to be for torque? Well, it's also newtons times meters, but it's not a joule. Even though a joule is a Newton meter, joule is only used for energy. Torque is not energy, even though it has the same units. So you do not put joule for your unit here. So your unit is a Newton meter, or as the people in statics use all the time, they use a foot pound.
That kind of seems like an arbitrary distinction. Why is it so inappropriate to use joules when it represents the same?
It's because joules represent the unit of energy. So it's a Newton meter, but it's the unit of energy. Because, I mean, yeah. Based on, if you break it down to the fundamentals, joule would be appropriate for torque, right? But it's not energy, so that's why it's not appropriate.
Okay. So it is an arbitrary distinction, but one that's like important and
Yeah, that's right. You can think of it as an arbitrary distinction because it's simply based on what we're measuring. And if you're measuring a different thing, you don't use the same unit, even though they mean the same thing. Okay, so that's the magnitude is R times F times sine of the angle between the two. Now I'm being a little bit careful here. I'll come back and talk about it a little more after the next part. But this is a vector product, so it has to have a direction. And how you get the direction, well, I have the perpendicular parts. So let's say I have like this and this. What direction would I assign if I have these two directions? Well, for the answer. There are two directions that would be meaningful. The two directions that are mutually perpendicular to these two. And so we choose one of those two for the direction for the answer. And how do we determine which one it is? That's where the right-hand rule comes in. So the right-hand rule is how we get the direction for the cross product. So for any cross product, if I have vector A cross with vector B gives me vector C, right? That's a very generic way of writing the cross product. you take your right hand and you align your fingers so that your thumb is perpendicular to both your index and your middle finger, and your index is perpendicular to both the middle finger and the thumb, and well, once you have those down, the last one. So they're all mutually perpendicular. Yes, orthogonal also works, yes. So, yes, it's an orthogonal system. Then, once you have that established, we make our rules. So you take the first item in the cross product and you align your index finger with the first one. And then you align your middle finger with the second one, and then the answer is the direction that your thumb points. So let's just have some fun. Here I have 5 kilograms. I think it's 5. Yeah, it's 5. So I hold it out here. The first thing is, what is R? Right? I haven't talked about what R is. R is the radius vector from the point I'm calculating the torque about to where the force acts. So traditionally, I would choose the pivot point. So my shoulder joint is where R starts, and then points to where the force acts. So what direction is R pointing? That direction. So you take your right hand and you put your index finger pointing that direction. Now I need to take, keeping the finger that direction, orient your hand so your middle finger points the direction of the force that's acting at the end of my hand. That's right, Max. Everybody be like Max. What direction is your thumb pointing, Max?
Towards me.
Okay, so that means the torque created by this about my shoulder joint is that direction. That's how the right hand rule works. Now we reverse it. We use my left hand. What's different?
Can I use my left hand?
No. The difference is your index finger is pointing the opposite direction, your middle finger is still pointing down, and now the thumb points this way. So reverse the direction by moving it one side to the other. No. No, it's not. What if I hold it like this? What direction is R pointing? What direction is the force? Can't make that happen, can you? There's no perpendicular components to begin with, right? So there's no torque in this case because the R and F are not perpendicular. What about like this?
Yeah, there's perpendicular.
There is a perpendicular component. My arm's getting tired, so I'm setting it down. I don't know, I choose a big mass because I feel like a big man. But then I get big tired. So here's another rule. Remember I said mutually perpendicular? Your middle finger can vary between here and here. Don't hyperextend. Don't put your middle finger up behind your index finger. But it can be anywhere in between. So when I was holding the weight up here, your index finger points that direction. And then you orient your middle finger so it points down. And the only way you can have it so your middle finger is somewhere between the index and coming opposite the index is like this, so the torque is still going that way. Whereas if I was holding it up here, R is like this. I need to orient my hand so the finger can point down, and it's going back.
Oh, that hurts the arm.
Try doing it with 5 kilograms.
Hold up. So you said the middle finger can go anywhere from here to here?
Anywhere from parallel with index finger to anti-parallel on the side of the palm.
Anywhere from, sorry, here
Yes,
to here.
that's correct.
So why couldn't we do it in the first place?
Well, because there were no perpendicular parts. They were parallel. And since we're multiplying the perpendicular parts, if you're doing like this, you know what you could do? You could go all the way around like this now, right? Because my index and middle finger are keeping the same. There is no way to define the direction. But since the torque is 0, you don't need a direction.
So why, for the example, is your thumb pointing towards you instead of your middle finger? Like, I don't
Okay, so the index finger is the first item in the cross product.
Right.
So looking at a cross product, and I should go back to our actual equation. Its torque is R cross F. So the first item is R.
Right.
Now don't come to the test with R written on your index finger, right? That wouldn't be considered cheating. You need to know that the first item in the cross product is your index finger. Second item is the middle finger, and then answer stuff.
Is it still cheating if we get a tattoo?
Yes.
I'm still confused on that.
Yes.
What are you confused about?
Like, okay, I get that R is my index finger.
Yes.
But why is the answer the thumb and the middle finger like that?
So it's a formalism to use the same relationship between directions every time.
Mm-hmm.
So you have two options. If you take your left hand, your right hand, if I have the same situation, so the mass is out to my right. If I put both index fingers right and both middle fingers down, the thumbs are opposite directions, right? So they just chose this one out of the two. Right? They could have done all of physics with the left-hand coordinate system, just would have, everything reversed. So they chose the right hand as the definition for how they're going to choose what direction you have when you're multiplying perpendicular vectors to get a vector product. And so then you have, based on that convention, the fixed rules of this is the first one, this is the second, and this is the answer.
Right, but why is your hand pointing like this instead of like this?
Because the definition has first one on index, second one on middle. If you reverse it, it would also reverse the direction. Right? If you flip any two fingers, it's going to reverse the direction.
Can you do another example?
Sure. I have some coming up.
I'm really confused about this.
I'm confused as well.
And so, yeah, as we do examples, hopefully the confusion will diminish.
Okay, so on the test, you're gonna be like, point your fingers here, and we're gonna have to write that down, like my thumb's pointing towards you.
On the test, you could have a question that says, in the equation A cross B equals C, what finger points in the direction of the vector C? You could have a question like that. Or you could have a question that says, if in this diagram or this word description, what direction is the torque? Right. One is a practical application of this specific equation. One is making sure you understand how cross product direction works. So it is something we need to learn. By the way, on the test, remember that your paper can freely move around. You don't have to sit here and try to get some odd direction. Just rotate the paper to make it so it's comfortable with your hand. So let's look at some practical examples. Let's start with this picture here. Let's say I want to sum the torques about this location, the one where I put a dot. So the first thing is always identify where you're summing the torques. If you are in static equilibrium, that means the sum of the torques is 0. The sum of the torques at any location will be 0. If it's not in equilibrium, then it depends on where you sum the torques, what your actual value is going to be. So this situation is not in equilibrium. I'm going to get a different result depending on where I sum the torques. So that's something important to keep in mind. If it's static equilibrium, which is what we're studying in this chapter, then it doesn't matter where you choose to sum the torques as long as you sum them all from the same location. But if it's not static equilibrium, it does matter. So in this case, we've determined, number one, where we're summing the torques about. Number two, we have to determine what the R vector is. So what was the rule on the R vector? Going from where to where?
From the point of pivot
Okay, from the pivot point to?
to where the work is done.
Not work is done, where the force acts.
Oh, yeah.
Work will be done, but if it moves, work will be done. If it doesn't move, work won't be done. So my R vector is going like, and of course I'm assuming the force is acting on the center of the stick. So there's my R vector.
So why that one and not the upper one?
Because I'm just doing the first one. I'll do the upper one second. So I'm going to do it too.
So
Excuse me? I had two questions.
Sorry, in the back.
So it would be like this, is that what you would want us to do?
I'm going to get to that. That's where I'm going next. First, I had to define what R is, and then we'll do that. What was your same question? Okay. So we have our R vector defined from the pivot point to where the force acts. That's called the lever arm, by the way. That's the name for it, the lever arm. So now I take my right hand, and since R is the first item in the cross product, it's R cross F. Then I make my index finger of my right hand point in the direction of R. So I'm going to make my index finger point like that. And then I need to orient my hand so my middle finger points in the direction of which item? The force. So for the lower force, the force is coming this direction, so I have to orient my hand this way. And then my thumb points toward you guys, so that's the direction of the torque.
Wait, go back. Why is the middle finger, why is it going the direction you said it was?
It's going the direction of the force.
And why is this one going up again? Okay, I get
That's going the direction of the radius. Right, the definition is your index finger is the direction of the first item of the cross product. And the cross product is so there's the first item, so that's the index finger. There's the second item, that's your middle finger. There's the answer, that's your thumb. So that's definitional. That's the definition of how we calculate a cross product. I say that's just linear algebra, but a lot of people didn't learn that. A lot of people haven't done much with vectors in their lives.
So the torque is pointing towards the back of the classroom. Why is it rotating sideways?
Okay, we'll get to that. We'll get to that. Question?
I'm not raising my hand.
Crap.
I didn't put a D. Why did we choose the force going this way instead of the force going this way?
I was just choosing one force. So I'm only doing the torque due to the lower force now.
So if I point my middle finger the other way, then my thumb's going out the other way.
That's correct. So the torque due to the lower force is going what direction? It's going toward the back of the classroom, toward the periodic table. Now we're going to do the torque from the second force. So for the upper force, what is my R vector?
It's going from the force all the way down to your bottom.
I would reverse that. It's going from the pivot point to the force, not from the force to the pivot. So there's my R for the upper force. So now, using the right hand rule, what finger points the direction of the radius? Index. So my index finger is going like this. And then what direction do I need my middle finger to point?
Same
Same as the force. So I need to rotate my hand, keeping that index finger the same, making my middle finger point direction of force, and what direction is my thumb pointing? In the front of the classroom. So this one here is making a torque to the front of the classroom.
I do not get. Why is the middle finger so going?
So if radius and if the R and force were switched to the cross product, would it be the other way?
Remember, force is the middle finger because it's the second one in the cross product. So you can't reverse it. You can't. Torque is not force cross R.
It's R.
It's R cross F. The order is vital.
Okay, isn't that arrow on the left-hand side the radius?
The blue arrow is the radius.
Oh, okay, I get it. That's not good.
So what, Claudia?
So, okay, so I'm starting my radius like this.
Yeah.
So that's my index finger, and then my force is gonna go up that way.
Right now you're doing for the lower force. Claudia is. Well, actually, you're doing Claudia, so yeah. Right now you're doing for the lower force.
And then
The upper force is like that, right?
Like this?
Yes. And remember, your thumb has to be perpendicular to both of them. Yeah, because some people will do things like this. Well, that thumb is not perpendicular to my index finger. It needs to be perpendicular to something. Okay, Oksana's been patiently waiting for the question.
Would it be a negative torque?
Okay, would it be a negative? It's positive in the direction of the thumb. And so, positive in the direction of the thumb, how do we define a negative here? We do define a negative. We did generally define that if it's coming out, it's positive. If it's going in, it's negative. So the one that was pointing out of the screen toward the back of the classroom, we would typically say is positive. The one that's going into the screen we call negative. You can also use a clock to determine that. See the second hand's going around in a direction we call clockwise. If it's going to make rotation in that direction, we call it a negative. If it's going to make rotation that's counterclockwise, we call it positive. We use our right hand once again to do that. If I take my fingers in my right hand and I wrap them the direction the second hand is going like this, clockwise, my thumb points into the clock, and that's negative if it points in. Counterclockwise, my thumb points out, and that's positive. So counterclockwise is positive, clockwise is negative. Yes?
Why were both of our radius going in the same direction? Like, why is
Because we were going from the pivot point to the force, and both forces were above the pivot point. Right, the radius is going from the pivot point to wherever the force acts. It's longer for the second one. Same direction. In this case.
Is the pivot point like arbitrarily chosen?
In this case, yes, I arbitrarily chose it. In some cases it will be arbitrary, in some it won't be. And remember, if it's in equilibrium, it's always arbitrary. If it's not in equilibrium, then it's not arbitrary.
Why are our torques in opposite directions? If it's
The torques are in opposite directions because the forces are in opposite directions.
So the reason this example isn't in equilibrium is because R isn't equal between the two different forces. Because
Right, because
this
R is
way
not
has a
equal.
negative, this is a negative torque, this is a positive torque.
And in fact, remember, the angle between the force and radius is the same in both cases,
Right.
but the radius for this is much smaller than the radius for this.
Right.
So the magnitude of this torque, which was the negative torque, is much bigger than the magnitude of the positive torque. So we have a net negative torque, which means it's going to rotate in clockwise direction.
Okay.
Yes, Andy?
Okay, so since the pivot point is below both of the forces, they're acting in opposite directions, but since our point's not in between them, then the torques are going to be in opposite directions.
Right.
But if it were in between them, then we would get the radius would flip.
Okay, so let's just do what Andy's saying. Let's do what Andy's saying. Let's sum the torques instead of about that bottom point, sum them about a point in between. So I'm going to sum them about a point that's midway in between. What? That video better be on topic. Okay. Okay, so we sum the torques about this blue dot now. So for the lower force, I'm going to call this force 1 and this force 2, just so we don't have any confusion. So what is the radius to go from my pivot point to force 1?
It's pointed down.
So there is radius 1. And so I take my index finger, and what direction should it point? The direction of which vector?
R1.
The direction of R. Now you have your fingers crossed. The index finger needs to be going straight out, and the middle finger, the index finger needs to go straight out with your hand. And then the middle finger bends toward the palm.
How do you, with the fourth
Wait,
one,
go.
how do you?
No, your index finger needs to go straight.
So maybe
The index goes straight, that's right.
That's going down.
And so you're going to point that down, that's right.
Yeah, but then how do you get the force to go that way with your middle finger?
Rotate your hand, keep your index finger in the same direction. No, so your index finger is bent now. Straight. Your middle finger is going this way.
I thought that was so, I thought the index finger was so long and aligned with the right.
Yes.
And the radius is the red arrow.
The radius is the orange arrow coming down.
Right.
But it needs to be straight with your hand.
But now I can't.
Well, your middle finger can bend this way. And so you rotate your hand so your middle finger points the direction of force.
Yes.
And then your thumb points into the string.
So force radius is.
Okay.
This is like arbitrarily supposed to be the middle.
I hated that.
I hate it.
Now, I usually only teach one way to do the cross product to avoid confusion. But because people are trying to use the fingers in the wrong orientations, let me go to the other way I was taught. Hold all of your fingers straight with your hand and point that in the direction of R. And then orient your hand so you can bend your fingers into the direction of F.
No, this is carve.
Oh, I like this better.
So for the lower one, if it's like this, I can bend my fingers into the direction of F.
Oh, into the direction, not against the direction.
Right, into the direction.
May I
That-
draw something to clear this up?
May you what?
May I draw something?
Sure.
Hold on, real quick.
Go ahead.
So, like, could you have a direction? I mean, let's say it's R is like straight up, right?
Mm-hmm.
And the force it's acting is like 1 degree off.
Uh-huh.
This, that still counts?
Yeah.
Or like 179.
That still counts, yes.
What?
But remember, the magnitude is times sine of the angle. So sine of 1 degree is very small. Sine of 179 is very small. So it's going to be very small torque. But you still get the direction with the right hand.
So how do we show that in a test? It's pointing that way.
You say using the right hand rule.
It's pointing like east. On a test, using the right hand rule is pointing back or forward, like how we write that down.
You say using the right hand rule, that gives me this direction.
But what if you don't know your directions?
Yeah, exactly. Exactly. I don't know my direction.
You start by defining your directions.
Oh!
Now, Oksana drew a right hand coordinate system. Has anyone ever wondered why this is a right hand coordinate system? Not because most people are right handed.
Because the positive's going out there?
Because it follows the right hand rule. Because x cross y equals z. So with this coordinate system, x cross y, how would I calculate x cross y? What direction should my index finger point if I'm doing x cross y? Yes. And then what direction should my middle finger point? Like direction of y. And then what direction is my thumb point? The direction of z. That's why it's called a right hand coordinate system. If you reversed x and y, then you have a left hand coordinate system because it would work if you use your left hand instead of your right hand. Okay, so is that what you wanted with this diagram? It's just
Because pointing to the wall and pointing away from you would be negative. Pointing towards you is positive.
what do you not get? It's important to get things. We come to class so we can learn things, not be confused.
Like, I get it, I just can't get, like, my hand to do, like.
Well, and remember, that's what I said, like, when you have it on paper, the paper can rotate so you're not doing fun things with your hand.
Yeah.
Well, this is
We're going down to Y, so it's been.
Question?
yeah, so while this is Z, this is Z. So just use that to.
Well,
How?
yeah, you still have the same right hand rule. It doesn't change it.
Can we go back to the hockey stick?
I don't know if that's right now.
Can I like ask you a question?
Yes, absolutely.
So,
We are not going to get to do any problems today, I can tell you that.
okay, so we were doing this one, but then you talked about this one where you like grabbing. So then if our pivot point were down here,
Mhm.
then we would have put our fingers facing the direction of force.
So start with the fingers pointing that direction.
And then it would go like that, so it would be
And,
that way.
right, we'd have like, okay, straight your fingers. You start with your fingers like this, and then you bend them like that.
Okay, so then it would be in that way. And then for the other one.
What?
Wait, no, if our pivot point's center.
Oh, it is, well, yeah, if your pivot point was here,
So radius is that way, so the force is that way, so then it's coming back out this way.
Correct.
And then the other force, it's that way. Wrap around, and then it's going that way. And then it's clockwise, so it's negative. And then this one's counterclockwise, so it's positive.
Yeah.
Okay. Well, I don't like it.
Judith.
When I'm doing the force one, like my thumb is going in the opposite direction. So I'm not sure what's going on.
Okay, so when you're doing the torque due to R1 and F1.
F1.
Okay, so you take your, going from this point, index finger goes this direction.
Yeah.
And then orient your hands, your index finger stays the same, but middle finger is pointing the direction of F. And your thumb should point into the screen.
So since you said like when we're using the whole hand thingy, like I'm pointing down and then you said to that our hand should close the force is going and it goes this way.
Right.
And so my thumb points that way.
Correct.
It's supposed to point that way.
That's right.
Okay. What? I thought you were
If we're summing the
I
torque
thought-
about this point, then you have R is this direction, F is this direction.
So I can't.
And so you start with doing it the second way I did, where you're going to bend your fingers. You start with your fingers all pointing this direction, and then you orient your hand so you can bend them that direction,
Yeah.
and your thumb
It's
points
going
in.
this way.
Okay.
Well, it's the opposite of what it was when we were down here.
Yeah. Okay.
Now, what about if we did for force 2? There's R2. Now we have index finger points up. Orient my hand so my middle finger can point in the direction of F2, and that's also pointing in.
Okay. Nice. It's pointing up, right?
R is pointing up, that's right.
Okay, then I tried me. Ah.
There you go. Okay, let's at least look at, right, this picture here, of course, is just illustrating what we've been talking about. C equals A cross B. A is the index finger going straight. B is the middle finger bent at 90 degrees. C is the thumb pointing perpendicular to both of those. Okay, so let's look at an example of the bicep muscle if you're curling your physics book. Now we're doing this in equilibrium. So if it's in equilibrium, that means that the net torque is 0. And furthermore, we're going to be doing this so it's not moving at all. The velocity is 0. Where should I sum my torques?
The elbow, right?
Okay. The answer actually, this is a very important thing for coming up. Obviously, our homework for today is going to focus on directions of cross products. You probably figured that out by now because that's all we covered.
Yes.
But when you're doing a statics problem, because your equation is R cross F, we have here 1, 2, 3, 4 forces. Let's say that I only know 2 of those forces. If I choose to sum my torques at the location where one of the force acts, then the R is going to be 0 and that force makes no torque. And I can have 2 unknown forces and solve with one equation for what the torque is. So when you're choosing where to sum the torques, always choose the location for one force that you don't know, because it's going to make that force make no torque. So I'm going to go with the answer that was given. Let's sum the torques about the joint. And we're going to say I want to find what the force of the biceps muscle has to be to hold that book up. So because it's in equilibrium, so the sum of the torques equals 0. And the sum of the torques is going to be raise the bicep cross force of the bicep plus radius for the center of mass cross the force of gravity plus radius of the book cross the force of the book, and then the one that I skipped plus radius for the elbow joint cross force of the elbow joint. So there I have the sum of the torques written out in long, gross detail. So then I need to look here and say, okay, this here is the radius for the bicep. I used B twice, didn't I? I used B for bookend, B for bicep. There, book is bow. So there's the radius of the bicep is right there. This is the radius to the center of mass. This is the radius to the book. So I have all those radii. What about the radius to the elbow?
It's 0.
Radius to the elbow is equal to 0. All of these radii are predicated on my decision of where to sum the torques. But given those, now what's the angle between my radius and my force of the book? 9 degrees. What's sine of 9 degrees? 1. And so that's the easiest case. If they're perpendicular, R cross F is just R times F in magnitude because sine of 9 degrees is 1. And likewise for the rest of these, are all 9-degree angles. What direction is the torque due to the force of the bicep? I'm going to start here. My R goes that way, so I need my index finger to go that direction. Then I need to orient my hand so my middle finger can point in the direction of that force, and it's coming out. Yes, I start with my index finger pointing the direction of R, so it's going that way. And then I orient my hand so my middle finger can point in the direction of the force, which was up.
Wait, I thought,
So R, then like this.
hand bending, my thumb's going that way. My thumb's going this way.
Right hand, right.
Oh.
Okay, so I will actually do this problem to start next class period.
Real quick. So
Yeah.
You said the torque was going this way, right? The direction of the torque is back to
The direction of the torque for this one is R cross F. That one.
So what would you call that in the test?
I would say there's multiple ways I can describe it. The most obvious is coming out of the page.
Oh.
Or I can define X is horizontal,
You're
Y
gonna
is
do this thing in
vertical, Z is coming out of the page. and
Okay,
Z
Riley,
is
you
right.
do the same thing. This and then with the hydrogen.
I could also
You get the
find, I
greatest
could say,
mass,
well,
the
that's
least mass,
counterclockwise.
until it's the left or right.
That also would be acceptable.
Really?
Wait, no, catch it.
You can because the force of that
Okay,
bicep
that's
is
pretty heavy.
You said
counterclockwise.
Grandpa's heavy.
Oh, that makes sense. Yeah. That's right.
Yes.
My hands aren't like large enough to.
All right, I gotta go to the calculus.
It's like the initial.
Oh, gosh.
Equal to.
Right, work is force dot distance.
I thought it
Oh,
The
that
one that we're working on torque is of that.
is a cross product, right?
Okay, well, we're gonna be late to Bible class.
So why the first one is the second one?
It goes to mathematical definitions, but the dot product is multiplying parallel parts. And it turns out there's no direction for that calculation, just from the way it's defined.
So since it's parallel, it's.
It's multiplying the parallel. I mean, one could say, well, they're both this direction, so shouldn't the answer be that direction? And if that was the way it's defined, but it's not. It's defined as this way.
Okay. And then vector is because, torque is defined as a vector because, like, we both have vector values in them.
Well, you can have
Claudia,
a rotation
have you done
cause
all the
in
homework
different
questions?
directions, and that's why we use vectors to tell us about the direction of rotation of the cause.
Yeah, okay.
And they don't want to be.
And by the way, so I am not going to see the class result because there's.
I thought you were reading this
class
chapter.
four.
I thought you were dating this like.
In class assignments.
No, not anymore.
So,
So you're not blowing me up.
I'm learning it.
Yes.
I have a question on the homework.
All right. Let me turn off the-
If we can do it in what in the world?
We could do anything in no time flat.
In like 2 minutes.
2 minutes, yeah.
Okay, we got this. We're supposed to write an expression. I wrote an expression.
And it was wrong.
And it was wrong. You wrote the wrong
My
expression.
expression was
Okay.
N1B1 divided by N2.
So let me see the problem. Which one is it? A student of this mass stands in the car. Okay. So we have
53 did on the cart. Which
mass of the person,
53. Cart is 1 foot.
mass of the cart. And so mass of the cart. I don't care what the numbers are because we need the
Oh, yeah.
expression for now. Okay, and we have initial condition is velocity of the cart, initial equals 0, velocity of the person, initial equals 0, right? Those are important as well. Okay, so then we have the person runs off, because that's genius. And so you end up with,
First of all, this was a stupid question because
Yeah, I would do it.
nobody would be on a cart.
I would.
the person going forward
Yes. Because
and the cart,
magically full.
It's going backwards.
well, yeah, magic. The cart must be going in this direction.
Yeah. Okay.
So what's our concept?
Mass.
Okay. Okay, so the concept starts with the sum of the external forces equals 0. That's really important because if it's not, then we can't do the next part.
Okay.
So because the sum of the external forces, what our system is the person and the cart.
Mm-hmm.
External forces in this case would be friction between the cart and the ground. And so we're saying friction between the cart and the ground is 0. So the sum of the external force is 0. So delta P is equal to 0.
Yeah.
Momentum doesn't change. So that's our concept. We have two pieces. The first one has to be satisfied for the second one to be true. And so in that case, momentum initial is equal to mass of the person, velocity of the person initial plus mass. I use O's and I's both for initial. Sorry, I try to be consistent. Mass of the cart, speed of the cart initial. Both of those were zeros. So the momentum initial was 0. And then momentum final is equal to the mass of the person, velocity of the person final, plus mass of the cart, velocity of the cart final.
Mm-hmm.
And then if change in momentum is 0, the momentum initial has to be momentum final, which means 0.
Mm-hmm.
So what am I trying to solve for?
V2. So
The velocity of the cart. So I'm going to subtract mass of the person, velocity of the person final from both sides,
Divided by MC.
and then divide by MC. So I'm going to have,
It is negative.
how did I do it work then?
I didn't do it.
Oh.
We erased it.
Okay, so I had the right thing, just didn't have it. Lobby M 1 3 1 That's it.
Thanks.
and you remember the my sign this time, right?
Yeah, so I had that all done. I just don't know why I didn't have mine. I honestly don't know why I didn't.
Alright.
Why? I literally subtracted.
Thank you. Thanks every day.
Uh-huh.
So, to my understanding, momentum is considered either inelastic or elastic.
It should be, yes.
So, when we did in this experiment, we did a group called after we did the first elastic. So, for the first trial, what we did was just change the mass. So, we just did it without the block. We did the inelastic condition where we stay together. But momentum doesn't seem to be.
Yeah, the only way that is if you have mass is wrong.
We had a maximum. We didn't switch from afterwards.
So-
we had it set for the first switch in the condition.
So what you can do, I mean, at this point, you don't want to redo the whole experiment, right?
Okay.
But what you can do is you can then make a notation. The mass on this was correct, the mass on this one was half of what it should have been. And so if I double, and you can explain it and then actually do the calculation to show that it's
would have been conserved. Right. I mean, that's all you can do at this point is use this data and use having the wrong mass to back out what it should have been.
Okay, can I just explain that because you have the wrong mass and
You have to do the calculation to show that that actually explains it.
I want to just that.
Well, okay, so
Let's just take a hypothetical. Mass 1 on the computer is equal to 0.5. Mass 2 on the computer is equal to 0.5. And of course, I'm just using one digit here because.
Yeah.
But in reality, mass 1 reality was 0.5 and mass 2 reality was equal to 1.
Mm-hmm.
And so what you need to do then is momentum 1 reality is equal to momentum 1 computer. I put momentum 1 computer because they had the right mass.
Mm-hmm.
But momentum 2 reality is going to be 2 times momentum 2 computer. Use M again instead of P because of having double the mass, right? The 1 over 0.5.
Because it's twice.
And then same thing with kinetic energies.
Can I take a picture of this?
Sure. No, this is proprietary.
This is if I don't write it down, and I don't have time to write it down, but
Right. This last one, that's how I did all the calculations.
Yeah.
Right. This had a 1, this had a 1, that had a 2. It came from that.
Got it. Okay. So then I don't have to do that.
And so then measure actual values to show that it will come out correctly.
Okay.
Right. So you'll have to say, okay, so right before the collision, momentum 1 was 0 and momentum 2 was this value.
What if I can get the exact?
It's not going to be exact. It's as close as you can read it.
Okay.
Right. Because that's what you're working with is the graph, right?
Yeah.
And then right after the collision, momentum 1 is this and momentum 2 is this. And then you correct momentum 2 and then you add them. Yeah. And of course, I don't know which mass was which. So when I'm pointing to this and saying it's mass, that's not meaningful. That's just saying one of them was wrong.
Okay. But when I think of the future, and kinetic energy should not have been conserved.
It depends on the situation, but just do the calculation and then make a determination based on when you did the calculation.
Okay. And then my other question was on the other two. So for cart 2, we tested inelastic collision, so we had both carts, and cart 1 had the block,
Mm-hmm.
and we kind of crushed them into each other, so they stuck together. But then they moved in the positive direction because cart 1 was heavier.
And I would guess that you have the masses wrong in this one too,
was wrong.
because your momentum jumped up at the collision.
Yeah.
That can't happen.
I don't know how that would happen though, because I think we had the masses right. For cart 1 it was do you have an okay for yourself?
Well, because the momentum jumped up, I'm assuming you have the masses wrong. This is all I can look at and make comment on.
Okay. So how would I
Well, it'd be the same.
do the same thing, like calculating and to make sure, and momentum should conserve and kinetic energy should not be conserved.
If they stuck together.
It's stuck together. And this is also wrong. This is elastic.
Yeah,
And maybe render
yeah, definitely
each other.
momentum went from 0 to something positive.
Yeah.
Doesn't make any sense. Everything is awesome.
Yeah, it gives me more to do. Okay, thank you.
So make sure you're very clear about what the problem is and how you checked it, and what your result is with how you checked it. Right, not just, and if I did this, it would have come out right, because who knows if it would have come out right if you did that. You have to do it. Yeah, I'm sorry that. I won't. as long as I can. And just longer than that. And you guys do have like 14 portions of yours. They do look fundamentally different, so you can tell the difference. Mine only have 2 styles. I think I know where they are. Okay. Hey.
Biology week. There's a big bee.
This big B, yes.
She doesn't stink.
That's good. That's good.
She's a giant bee, yes. Yep. She doesn't stink. Ellie. Just saying hi. All right. Sherry had your stamp upstairs, so I'm gonna send it to you to go pick them up. Yeah.
Okay, today's lab, we are looking at momentum